Hi, this is ET250 Lecture 8. And today what we're going to do is just go over a list of the midterm 1 concepts and then just a ton of example problems. All right. This is basically a summary of what we covered so far. The first lecture we talked about physical quantities versus units. There was 4 things. There's this unit or the physical quantity, the symbol for the physical quantity, the unit, and then the symbol for the unit. And so making sure you understand the differences between all 4 of these things, I think is very important. We talked about charge, and then we also talked about their hydro analogy for electricity to water. So charge is like water, current is positive charge flow or flow. Resistance is like a rusty pipe, voltage is like pressure. And so these are all, of course, very critical to your understanding of circuits and electronics. And we tie everything together via Ohm's law, right? V equals plus or minus IR. The other thing that has the plus or minus is power absorbed. P equals plus or minus IV. And remember, we had our equations for any element, P equals plus or minus IV, but for a resistor, you can use I squared R and V squared over R, always positive. We talked about independent and dependent sources. So independent, you have a current and voltage source. For dependent, you had these 4 flavors: voltage controlled voltage source, current controlled voltage source, voltage controlled current source, current controlled current source, right? Of course, KVL and KCL. And then we have equivalent resistors in series and parallel. Voltage divider, current divider, don't forget the plus and minuses on these as well. Nodal analysis, a combination of KCL, nodal Ohm's law, and then if you get simultaneous equations, you can solve it using the linear algebra matrix, right? Just punch in your TI-89 gives you an answer. Thevenin, the last 2 concepts were Thevenin Norton equivalent, just to simplify a circuit, and then finally superposition. The last thing, forgot to mention, switch, open and short. What are the consequences? For a shorted condition, you have 0 voltage, but any current. For an open circuit, you have any voltage, but no current, okay? Of course, there's a much more detail that's going around, but these are just kind of the headers, right? All right, so let's spend the rest of this lecture just going through examples. So no new concepts, just crunching problems related to this, okay? So let's look at this first example. So this first example has 2 resistors on the top in parallel, 2 resistors on the bottom in parallel. We're given the voltage, we're given all the resistor values except for this Rx. So that's one thing we want to find. We're given this current is 2 amps, and we want to solve for I1, I2, and this total I. Okay, so we look at, well, if we're given this current, we could probably solve for this voltage V3 here by Ohm's law. Once we have that V3, we could probably solve for Vx because they're in parallel. So they, we know Vx is the same as V3. Once you have V3 and Vx, you could also solve for V1 and V2. So V1 and V2 are going to be the same because they're in parallel, but you could do a KVL all around this loop here, because if I know 12 volts and I know V3, I could easily solve for V2. What else would we get? Well, if you know V2 and V1, since they're the same, you could do Ohm's law and get I1 and I2. So that would solve these 2. And once you get I1 and I2, you could do a KCL here at the top node and solve for I, right? Because boom, boom, KCL, these are 2 nodes and this is unknown. And that would actually be the problem. So that's kind of nice. We didn't write out any equations. We just talked about strategy. And right away, we can see clearly what our strategy would be. And this kind of helps me out so that when I'm crunching, I'm not just writing down equations. There's kind of a little bit of a method to the madness, right? So let's start out with what we do know. So we can say Ohm's law. So I'm always going to put the law. So V3 is equal to positive I3R3. Okay, so what do we have? I3R3. We know I3. We know R3 good. So V3 is equal to 2 times R3, which is 2. So V3 is equal to 4 volts. Good. Okay, what else? We know by KVL, Vx is equal to Ix Rx, right? And so we know this is equal to 4 volts. Okay. So once we get Ix, which we forgot to talk about, but Ix looks like if we know I3 and I, we could do a KCL and solve for Ix. Then you go apply this Ohm's law and get Rx again, right? Okay, so we're going to hold on to this equation. And we're going to say Rx is equal to 4 divided by Ix. So we're going to hold on to this. So once we solve for Ix, we'll come back here and get this answer. But let's keep going. So what else did we say? We said once we know V3, once we know 12, we can get V1 and V2 because they're the same. So let's do a KVL. And we can say minus 12. Let's just do the outer one. Plus V2, minus 12 plus V2 plus V3 is equal to 0. We know V3, which is 4, so we can say V2 is equal to 12 minus V3 or 12 minus 4. So V2 is equal to 8 volts. Good. Okay. So once I know V2, by Ohm's law, I can get I2. So I'm going to put this over here. So I2, so V2 equals I2 R2. That's good. And so what do we have? I2 is unknown, right? But R2 is not unknown. It's known here. So I2 is equal to V2 over R2 is equal to 8 divided by 8. Is that right? Looks right. Okay, so I2 equals 1 amp. Yay. So this is done. Check. What else? We can do the Ohm's law there. Ohm's law, V1 is equal to I1 R1. Again, all these are positive, positive, positive. Yep, 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 all going to the positive terminal. So I1 is equal to V1 over R1 is equal to V1, which we know by KVL, V1 is equal to V2. So notice I'm writing every single step down. So V2 is 8, V1 is also 8, right? Divided by R1, which is 4. So I1 is equal to 2 amps. Excellent. Okay, so we've knocked out this one and this one. Okay, what's next? We could do a KCL. And so KCL, we could say I is equal to I1 plus I2. No problem there. Okay, what else? I is now equal to the sum of these two. So it looks like 1 plus 2. Okay. And so we have I is equal to 3 amps. Fantastic. What's next? We have I done, I1, I2 done. So we could now come back here and do this KCL maybe on this point and then solve for this IX, right? So KCL again, we could say at this node, IX plus I3 equals I. Currents entering equals currents leaving. Okay, so IX is equal to I minus I3. So in this case, I is 3 minus I3, which we were given as 2. So IX is actually 1 amp. And finally, we come back to our original Ohm's law equation here, and I can say that Rx is equal to 4 over 1 equals 4 ohms. And that should do it. That should do it. And does that match my solution? It sure does. So that's nice. So again, we don't ever just end it and move on. We just double check. Do these numbers make sense? So we would have 4 ohms here. We got a 12-volt source. So if we got a high voltage here, I would assume current's going to want to trickle down this way. And it looks like all these numbers, I1, I2, and I are all positive numbers. That seems to make sense. There's nothing crazy, no crazy values like 3,000 amps or 10 amps. It's like, okay, these are all within the right order of magnitude. And then this number here came out to a positive number. That's important. And is it within the range of these other numbers? Yeah, 4, 8, 2. You're not like getting kilo ohms. So yeah, I think I'd buy this kind of this system and all the system of numbers that we got. Okay, now I'm comfortable with moving on. All right, so let's put this over the side. Okay, solution is here, same thing. But now let's go and do the next problem. The next problem has a dependent source, okay? And the question asks, find this voltage here. All right, so what are we given? Oh, it looks like they gave us this current. So the current in this branch, both of these are in series. All these elements are sharing the same 1 amp worth of current, okay? They gave us that number A, which is 0.5 amps per volt. And this looks like a voltage controlled current source, right? It's a current source here. And so let's write that down. So this is a voltage controlled current source. And the equation would be ID is equal to AVX. which is equal to 0.5 Vx because of that number there. Okay, that's good. So if we were trying to find Vs, how could we solve for it? Well, it looks like a KVL would help, right? So if we did a KVL around the whole loop, it looks like if I had this voltage and this voltage and this voltage, that would give me this one. Well, how would I get these voltages? Well, if I know this current and I know this resistance, I could get Ohm's law to give me this V2. Okay, that's good. I could do the same thing here. I know this current, so I know this resistance. Great, I get Vx. Oh, almost there for that KVL. So Vx would be known pretty easily. V2 would be known pretty easily. Great. But this current is not the same as this current. But could I get it? All right, well, let's look at our dependent source. Okay, I know, oh, if I know Vx, I actually know ID because I just take whatever number times 0.5. That's this current down here. Oh, that's nice. If I know this current, I know this current, I could apply a KCL and get this one. And once I get this current, I get this voltage via Ohm's law, and then I can go back to my KVL around the whole thing and get Vs. Excellent. Let's apply it. So let's write these down. Ohm's law. V2 equals positive 1 times 2. So V2 equals 2 volts. Let's do this one. Vx is equal to positive, yep, goes into the positive terminal, 1 times 4. So Vx is equal to 4 volts. So this is also Ohm's law. Okay, great. So I have Vx and V2. Back up here, I can say Vx, if I plug that in, so ID is equal to 0.5 times 4. So ID is equal to 2 amps. Great. So then once I have ID, I do a KCL and I can say ID plus 1 is equal to IS. So IS is equal to 3. 2 plus 1 is equal to 3 amps. Great. Once I have this, I get Ohm's law, V3 is equal to IS times 3. So V3 is equal to 3 times 3, 9 volts. Great. And the last, we'll do at KVL that we talked about. So KVL, I'm going to say minus Vs plus V3, and then let me show that, plus Vx plus V2 equals 0. Minus Vx plus V3 plus Vx plus V2 back is equal to 0. Great. And so I can just bring this Vs to the other side. So Vs equals all of this. So V3, which we solve as 9, plus Vx, which we solve for as 4, plus V2, which we solve for as 2. And so Vs is equal to 9 plus 4, 13. 13 plus 2 is 15 volts. And that's the final answer. Okay, so we have 15 volts here. We have positive currents flowing through here, high pressure kind of pushing down. Okay, that seems to make sense, right? Currents coming down here. Yeah. Let's see if that matched. Yep, that also matched my solution. Yay. Okay. Not too bad. Let's go to the next problem. So this next problem is very similar, right? We have a dependent source, 2 resistors, independent source. This is a current now. This is a, what is this? This is a current controlled current source. Okay. So I could do the same thing. I could say AIX equals something. So let's crunch through. So put this on the side. And they tell us that A is 0.5 and it's unitless. Does that make sense as unitless? Because you're going from amps to amps? Yeah, we're okay with that. And they gave us a bunch of values here. So they told us what V3 is this time. Instead of the I, they told us V3. Okay, so this B, they want us to solve for this IS. They want us to solve for Vs, which is the voltage across here, and Ix, which is this current in this branch. Huh. So what do we know? What do we know? We know that, let me put here, I want to give this a name, ID again, just like I did here. So we know from the current controlled current source, ID is equal to AIX, all right, which is equal to 0.5 IX. So we'll hold on to that. We know this voltage. I know this resistor. Oh, that's like Ohm's law. For free, I get IX. Great. So that's actually one problem solved. Once I get IX, we can play that same game, Ohm's law. If we know R2 and IX, we're going to get V2. Okay. So that's nice. Oh, look at this. If I know Ix, I also know ID because I just take this Ix, multiply it by 0.5, and I get ID. And then I can apply the KCL again. Boom, I get whatever Is is. That's that solved. If I know Is, I can solve for V1 via Ohm's law. And once I get V1, I can do a KVL around the entire loop and get Vs. Nice, because these three would be known at that point. Okay, let's crunch it. All right, so we have this V3 here, we know it, it was given to us at 20 volts. So Ohm's law, V3 is equal to Ix times R3. Positive current's going to the positive terminal, good. So Ix is equal to V3 over R3 is equal to 20 divided by 20. So Ix is equal to 1 amp. Good, so that's done. Okay, we go to our V2, Ohm's law. V2 is equal to Ix times R2. So it's equal to 1 times R2, which is 10. So V2 is equal to 10 volts. Nice, nice, that's done. Okay. What's next? We can go back to here to this current controlled current source. And since we know Ix, I'm going to plug that in here. So this is 0.5 times 1. So ID is equal to 0.5 amps. Nice. We can go to the bottom here and do a KCL and get this Is. So KCL would say what's coming in, this ID and Ix. So ID plus Ix is equal to Is. So Is is equal to ID, which is 0.5, plus Ix is 1. So Is is equal to 1.5 amps. That's this one, done. And the last thing we have to get is that Vs. So what do we need? We can do an Ohm's law there and do a KVL. So what do we have? Ohm's law. So this one, V1 is equal to Is, positive Is times R1. Is is 1.5 times R1. It was given 15, good. So V1 is equal to 1.5 times 15. What's that? Is that 20? I think that's 20, right? Okay. So, yeah. All right. No, that's not 20. That's not 20. It's half of 15 is, what are we, brain farting here, 7.5. This is going to be 22.5. Right? Okay. So then we have this one here, and then let's see, KVL is going to give us the final voltage here. So minus Vs plus V1 plus V2 plus V3 is equal to 0. So Vs is going to be the sum of all these guys, V1, V2, V3. And so what do we have? 22.5 plus V2, which is 10, plus V3, which is all the way over here, given 20. So Vs is equal to the sum of all this. So this is 30. This is 30 plus 20 is 52.5 volts. Okay. Oh, nice. That matches actually my solution. But let's just double check. Does that make sense? If we're getting positive currents through here, yeah, this better be a pretty high voltage. Yeah, it's good that this came out to a positive sign. All right. And then these are 20, this is a 20 volts. So whatever this is has to be bigger than at least 20 volts. And then you got these other resistor drops, these voltage drops across the resistor. Yeah, I buy that. That seems to make sense. Okay, good. All right, let's keep going. Ooh, a superposition problem. Superposition problem. Okay. So this is asking to solve for this current using superposition. You could use any, KVL, KCL. Could you use current divider? I think you could use current divider. If you knew the total current going into both of these resistors, which is a little tricky because you have these two, then you could sure enough use current divider. But since we have two sources here, superposition could work because you could just analyze it one source at a time. The first step always is checking linearity. Yep, these are all linear elements, no weird dependencies, no squares, no cosines, no sines. All right, we could do that. We say n equals 2, so we're going to solve for this current twice. So I immediately write I1 plus I2. And now we just go ahead and pick one, kill the other, pick one, kill the other. So let's go with I1, and let's say we keep the 4 amp and then the kill the 2 amp. So what are we going to have? We're going to have something that looks like this. And to kill a current source, we have an open. So this is the 15, the 5, and we call this I1. Notice I make I1 here in the same direction as the original I. Good. So this is the 4 amp, this is the 5 ohm, this is the 15 ohm. Now we can definitely use current divider. Current divider is easy. So I1 is equal to 4 times the opposite, 15 over 5 plus 15. And is it positive? Current's going in the same direction? Yes, it's positive. Okay. So I1 is equal to 4 times 15 over 20, right? And what do we have? We have 15 over 4. 4 over 20 is that 5. So this looks like I1 is equal to 3 amps. Good. Okay, let's do the next one. So we can say by keep this one, kill that one. So I'm going to redraw it. So this side is the open. And now we have the 5 ohm and the 15 ohm and the 2 amp. So this is 2 amp. This is 15 ohm, this is 5 ohm. And now I still keep this in the same direction, but now I call it I2 because we're solving for the second current. Later we're going to add it. Okay, so now we look at this I2. Again, we could use current divider. Current divider. I2 is equal to what? Minus, because in the opposite direction, 2 times, again, the opposite resistor, 15 over 5 plus 15. Okay, so I2 is equal to minus 2 times 15 over 20. Is that right? Yes. Okay, what's 15 over 20? Isn't that 3/4? 3/4. So I2 is equal to minus, and then we got a 2 and a 4, so isn't that 3/2? So isn't this I2 equal to minus 1.5, something like that? 1.5 amps. Okay, so then the final thing we could say I is equal to I1 plus I2 is equal to 3 plus negative 1.5. Oh, that looks like I is equal to positive 1.5 amps. So that would be the total current here. Okay, if I look at my solution, I get the same thing. Good. What do we have here? 1.5 amps is coming down. And if we look at this, it looks like 4 amps is going to come in, and that's going to overpower this 2 amps going in the opposite direction, right? And so, yeah, okay, I buy that this current's going to be positive going down, right? If this was a bigger number, I'd probably question whether this current was actually going down, but it seems like, yeah, that seems to make sense. Okay, so 1.5 amps going down. Yeah, total. And it's good to see. The nice thing about superposition, you actually get to see the contribution of each of the current supplies. You can see this 4 amp is contributing 3 amps going down, whereas this current supply is contributing negative 1.5 amps going down, or positive 1.5 amps going up, right? And so that's a kind of a benefit of superposition, is not just the ease at which you can solve easier problems, but the intuition you gain from how each independent source is affecting the overall answer. Kind of cool. Okay, let's keep going. All right, so here's a little bit of a messier problem. We have, wow, we have a dependent source here. We have this weird, like, double circuit thing. It's just connected by this weird line, right? They gave us the A, it's 25 amps per volt. What else did they give us? They said, okay, so you have this current here. They tell us that the absorbed power through this resistor here is 16 watts. Oh, that's a weird one, okay. What else they gave us all these resistors, R1, R2, R3, R4. Okay, so we have all these numbers, good. And the question is solve for I. What's I? I is this one. Okay, that's this branch. I2, okay. IX, oh, that's the current in here. And V in, this one here. And if I look at this dependent source, this current here is dependent on this voltage. So that's how they're bridged. See how there's an open circuit here, and you're only connecting this one lead? If there was no dependent source, these would operate nearly as independent like systems, right? Yeah, maybe the voltage here, the node voltage is the same as this node voltage, but there would be no current that would flow back here. Okay, so it'd be kind of silly to have this, but or be analyzing this. It would just be two independent things. But for this, yeah, okay, since the dependency, that's like the bridge between these two circuits. Huh. So we want to find all these things. It's a little bit of a complicated problem. We have to find a few things, but let's just kind of think about what can we attack. So they tell us that this is a positive current. So with the way it's defined as positive, and they tell us the wattage, the amount of power being absorbed by this resistor. So we could use that power law, that power equation, P equals I squared R, because it looks like we're not given V4. So that would allow me, I could do the P equals I squared R. I could divide this by the R and then do the square root and then get I4 and take the positive version. Okay, so that would give me I4, great. So if I had I4 and I have the resistor, oh, I could find V4. That's nice. So if I get V4, what else do I get for free? By KVL, looks like I get V3. If I get V3, what else do I get? If I know R3, good. I could get I3 via Ohm's law. And if I know I4 and I3, what else could I get? I could get I. So that's nice. So that means I can get I4, I3, and I know that this is a voltage controlled current source. Do they tell me A? Yes. So if I know this I and I know this A, I could actually solve for Vn. That's nice. So that means this is check and this is check. And then once I go over here, that means I know this voltage. Once I know this voltage, then what? I can figure out what this current is, I1. Great, I could use Ohm's law again. Once I have I1 and I have this voltage, what else? Well, if I know what this voltage is, I know what this voltage because they're in parallel. So that means I could do an Ohm's law here and get I2. And once I have I1 and I2, I could solve for IX. And so that would knock out these two. And that would be the problem. All right. Why don't we go ahead and attack? So let's start here. So we know power absorbed equals positive I squared R for a resistor. And so this case, it would be I4 and R4. Okay. So we know R4, we know power absorbed, right, for the R4. So I4 is equal to the square root of P absorbed 4 over R4. And we're going to take the positive version because that was given. Okay, so now I can plug in the numbers. What is it? Square root of 16 over 4. Okay, so that reduces to the square root 4. This is equal to 2. Okay, so nice. They gave us some nice numbers. Positive 2 amps. So that is I4. Great. We know by KVL, we can say V3 is equal to V4. Great. So that's equal to, well, we didn't solve it yet. We've got to say Ohm's law. V4 is equal to I4 times R4, which is equal to 2 times R4, which is 16. So that's 32. So that's nice. So this is 32. Okay, so we have this. So we have this voltage and this voltage. Then we can solve for I3 using an Ohm's law again. So V3 is equal to I3R3. So I3 is equal to V3 over R3 is equal to what? 32 divided by 32 over here. Nice. So I3 is equal to 1 amp. Okay, so that's nice. Good. So what do we have? I3, I4, and I. So by KCL, we have I3 plus I4 equals I. So I is equal to I3, which is 1, plus I4, which is 2. So I is equal to 3 amps. Fantastic. And is that one of them? Yep. We can write down the, what do you call it? The equation corresponding to this dependent source. This is a voltage controlled current source. So voltage controlled current source. And we can say AVIN is equal to I. AVIN is equal to I. So VIN is equal to I over A, or 3 divided by A, which is 25. Okay. All right. So what's next? So this is that voltage here. Okay, good. What is that? 320. That's not going to be a clean number, is that? I don't think it is. No. Well, we can just leave it as that. Or we could punch out the decimal. Do I have my calculator handy? Here's my next calculator. There we go. What's that rough number? 3 over 25. 0.12. 0.12. Vn is equal to 0.12 volts. Okay. So let's box that. All right, what's next? So we have Vn, we have I. Now we got to go over to this side because we now know this voltage, and it looks like we can now get I1 and then same voltage. Okay, so put it to the side. So I can use my Ohm's law over here, and I could say Vn is equal to I1 times R1. So I1 is equal to Vn divided by R1 is equal to 3 over 25, that's my Vn, divided by R1. What's R1? R1 is 5. Not really going to help me in terms of nice cancellations, is it? No, I don't think so. So I1 is going to be what number? 3 divide this by another 5. Very small, 0.024 amps. Yeah, okay. All right, so that's I1. And then I know by KVL, these two voltages are the same. So V2 is equal to VIN is equal to this one, 3/25. And then by Ohm's law, I have V2 is equal to I2R2. So I2 is equal to V2 divided by R2 is equal to 3 over 25 divided by 2. So I2 is equal to 3 over 25 divided by 2, 0.06 amps. Okay, so that's good. We're done with that. And because I have this one, I can finally use my KCL and get for the IX. So we have IX is equal to, so this is the current leaving, these two are the currents entering, I1 plus I2, which is 0.024 plus 0.06. So IX is equal to, is that 0.03? Oh, no. This is 0.06, that's here. So IX is equal to 0.084 amps. Okay, smaller current, but maybe the idea is that this is like some control circuitry with some smaller currents, and this is kind of like the output with some bigger currents, right? All right. Let's see here. Did I do this correctly? Let's see if I did this correctly. V3 here. V3 looks like it's 32 volts. Is I4 correct? Yeah, 2 amps, yeah. Unless I did something wrong here. I think this is right. Yeah. I might have gotten something wrong in my solutions. Let's check here. So I have 16 here, and then I says this is 16 equals, ooh, I made a mistake. The R4 is 16 ohms and not 4 ohms. Oh no, but I think the process is correct. So that means this changes this to a 16. All right, so what do we got here? We got this as a 16. Ah, so this becomes 1. Oh my gosh, we done messed up. All right, so this becomes 1 amp. Good, but the process is correct. All right, so then what's next? So now this is half of that. Yep, 16 volts. Yep, 16 volts. What's next? Oh, yep, so we still do the Ohm's law. Look, I'm doing the same process, just everything is 1/2, 0.5. Good, and then what's next? What's wrong? We have the I equals 1/2. Yep, good. And then the Vn, look at this, everything's half. Oh my God, oh my goodness. Oh well. Well, you know what? Part of this is just making mistakes and recovering from them, and then just making sure that everything is great. Okay, 0.03, good, and then half, good. So I'm okay with that, you know. Just made a mistake here with this resistance. If you made that similar mistake on a test, you know, you're not going to lose very many points. So that's good. Now, would that have been easy to catch? That would have been hard to catch, like to get to this point and to catch this unless you're willing to go back through and just double check all your work, right? So how could we check that? Well, the problem is, you know, getting 2 amps versus 1 amp, there's not very many what do you call it, red flags that are going to pop up, because you're like, yeah, okay, that's a positive number, that seems to make sense. Yeah. So yeah, you know, sometimes it's just about checking what it was originally given you, but otherwise this is all the correct process. Good. But this is the true answer. Apologies for that, but I'm glad you got to see the process correct, right? Okay, moving on. Let's go over and check out this problem. So this problem is actually out of the West Valley packet, and I like this problem. This is a kind of an interesting one where it asks you to solve for this IX. Now, the way they ask you to solve for the IX is they say take this part and reduce it down to a Thevenin Norton from the perspective of these A and B, right? And then once you've reduced it down to your Thevenin Norton, then put your 12 volt back in and then solve for it. And I'm going to add one more. Let's use superposition to solve for that Thevenin voltage. So we're combining here a Thevenin and a superposition together, kind of what I was talking about in class. Okay, so we're going to solve for that IX with a new simple circuit. What we're also going to do is just directly solve for IX using, let's say, nodal analysis, right? And we want to check if we get both answers to match. Okay, let's go ahead and do the Thevenin Norton reduction, and then we're going to do the nodal analysis. Okay, so at the end of the day, what we're trying to do is do this. Well, at the end of the day, we're trying to get IX, but let's go and do this first one. It sounds complicated, but I think if you just follow my logic, it's not too bad. Remember, you can take a complicated circuit and reduce it down to a simple circuit. In this case, we're going to choose the Thevenin over the Norton. We could go the Norton, but let's try the Thevenin. So I want to replace this entire circuit with this simple circuit. Cool? I can easily get the R equivalent, but then I also want to get the V Thevenin, right? Once I have that, because if this is, remember this, the idea is this circuit is equivalent to this one. This would be easy to solve for X. I could just do nodal Ohm's law, right? Look, IX equals VT minus 12 volts over R equivalent. Once I know these two numbers, that's easy. Okay, so let's go first and get this R equivalent. That's pretty straightforward. No dependent sources, so we can do that. We can kill all the independent sources and then solve for it. Notice at this point, the 12 volt is out of play. So don't worry about it right now. You're just worrying about this side here, okay? And we're gonna find the equivalent resistance between A and B for this circuit. So that's an easy thing for students to get confused. This is the equivalent. So we're gonna kill these three things and then solve for what's the equivalent resistance for that, okay? So I'm gonna redraw it. So we have an open here, a short and an open. Good. Open, short, open. Fantastic. And look, I have the 6 ohm, 3 ohm. Oh, this is about as easy as it gets. 2 resistors in series, and then we have 6 plus 3, 9. So this is 9 ohms. Done. Easy. Okay. Don't forget, this 12 volt is not in play. Don't short this and try to find the equivalent resistance, because that would just give you 0. Don't do that. We're ignoring the 12 volts right now, okay? All right, good. Now let's do the Thevenin voltage. Okay, so this is our circuit. Remember, don't put that 12 volt, and we want to find the open circuit voltage here. And now if I see 3 sources, I might go, well, why don't we use superposition and straight up solve for that VOC? Okay, so what do we got here? We have a linear system. Yes, everything's linear. Good. Check. How many sources? 3. 1, 2, 3. Okay, so that means this VOC is going to be VOC 1, 2, 3. Good. Check. So now what do? We can keep 1, kill 1, solve for VOC 1. Keep 1, kill these 2, solve for VOC 2. Then Keep this one, kill these two, solve for VOC3, add them up. And hopefully we get some pretty easy, simpler systems to solve. Okay, so let's keep the 4 amp. So if we keep the 4 amp and kill these, what do we get? So we have, let me redraw it. So we're going to keep the 4 amp. And we're going to kill this. So kill, this is open. And short this, good. So this is the 3, this is the 6, and we're going to call this VOC1 because this is the first one. Okay, so VOC1, we're going to keep the 4 amp and kill the rest. Okay, so we have the 4 amp here, and we want this voltage here. You might think it's a little tricky, but it's actually not that bad. Watch this. Is there any current through this 3 ohm resistor? This is open and this is open. Open circuit voltage, open here. So there's actually no current. I equals 0. That means by Ohm's law, V equals 0 across this 3 ohm resistor, which means by KVL, this voltage here, plus or minus, we'll call it V6, is equal to VOC1. Nice. Oh, that's beautiful. Ohm's law. VOC1 is equal to 4 times 6 equals 24 volts. Yes, it was a much easier problem. Okay, let's do the next one. Let's say VOC2. We're going to keep the 1 amp and then kill the rest. What do we got? Keep this open, short. Okay, so what do we have? We have open. We have the 6 ohm. We have the 1 amp. And we have a short, and we have the 3 ohm, and we want VOC2. Notice the same polarity as the original, okay? Any simplifications? Ooh, we have the same one here. I equals 0, right? Open circuit, therefore this V6 equals 0 by Ohm's law, right? So that means this VOC2 is the same voltage across this resistor and this current supply. So we'll call this V3, and by KVL, V3 is equal to VOC2. Nice. And by Ohm's law, check this out. Ohm's law, VOC2 is equal to 1 times 3 volts. Easy. Boom, boom. Okay, we got one more source left. This one, kill these two. Do I have enough room? I think I might even have enough room. So VOC3, what do we have? Open, 6, open. This is now there. So 6 volts. 3, so this is an open, and this is 6. All right, and this is VOC3. Okay. Let's see if we got anything nice to simplify. Is this open circuit? It is. And this is also an open circuit. So both of these have I equals 0. Therefore, by Ohm's law, V3 equals V6 equals 0. That means that this VOC3 by KVL, if I did a KVL, can you see that VOC3 is equal to -6 volts? Nice, right? Because look, the positive touching the negative, negative touching the positive. Good. So the final voltage here, this final voltage is just the addition of 24 and 3 and -6. So VOC is equal to 24 plus 3 plus -6, which is 27 minus 6, which is 21 volts. Okay, so that means if I go all the way back to this original system here, I can say that I'll plug my new reduced system. So this is a 9 ohm, 21 volt Thevenin, right? And what does that mean? This 9 ohm, 21 volt Thevenin is equivalent to this mess. And now I can take my original 12 volt source and put it in here and solve for this IX, and I can use my Nodal Ohm's law. So IX is equal to 21 minus 12 over 9. Is that right? So IX is equal to 21 minus 12. That's 9 over 9, 1 amp. So that means we have 1 amp in this system flowing from A to B. Okay. Does that make sense? Well, from the Thevenin, it's easy to see. You have voltage going this way, pushing current down this way. As long as this voltage is greater than that voltage, yeah, we're going to get current flow. It's a little harder to see in this one, but you have 4 amps kind of pushing down here, right? And you also have current going up. Yeah, you could see how this is, going to force current to come down, right? It's going to want current to go down into that IX. Okay, yeah. You can also, the nice thing about going through that Thevenin process, you can see how these what do you call it? Different sources affected the they affected the total of voltage, right? Or sorry, the VOC voltage, right? So it looks like this 4 amp would have created a positive voltage here. This 1 amp is also going to create a positive voltage here, whereas this 6 volts creates a negative voltage here. So this actually would hurt you. So again, the nice thing about superposition. Okay, now the last thing we want to do is we want to see if we applied just a nodal Ohm's law. So let me go to the next page. Okay, so this is just the answer. Good, 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 good. Good, 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 good. Here it is. Let's go. We go back to the original system. Can we just solve it straight up? Don't do the Thevenin, don't do the superposition. We sure can. We sure can. And what was the answer we got? 1 amp for this IX. Let's see if we just solve it straight up, do we still get 1 amp, right? By the way, you could straight up solve this IX using superposition directly. Don't even do the Thevenin, stuff, and then superposition and get to here, right? But anyways, let's just solve it using, let's say, nodal analysis, right? Okay, what do we have here? We have some node voltages, and I arbitrarily put a ground here. I could have put the ground anywhere, but I put it here. What do we notice? We notice that this node voltage, by coincidence, is actually going to be 12 volts. So by KVL, we can say V equals 12 volts. A V prime, a V double prime, 6 volts. Oh, by KVL, you could actually say that V double prime is equal to this voltage here plus 6. Okay. And you could do it formally. Remember, V prime is minus plus. So you could say minus V prime minus 6 plus V double prime equals 0, right? If you went around that loop. And so you could see that V double prime is equal to V prime plus 6, and you get the same results, right? Okay, good. So we have that. What else do we have? We want to solve for this IX. So that tells me a KCL here is in order. So IX, this is leaving, is equal to I6 plus 4. All right, so I need these two currents. So if I know I6, I'm done. I get IX. What else? Oh, I could do the KCL here, and I could say 1, so this current goes in, equals I3 plus I6 plus 4. Great. Okay, what else? Nodal Ohm's law. I could say I6 is equal to V prime minus V divided by 6. Yep, good. And I could say I3 is equal to what? I gotta be very careful. Wouldn't it be, if I didn't write this V double prime, wouldn't it be so tempting to write 6 volts here? It sure would. But 6 volts is not the same as V double prime. 6 volts plus V prime is the same as V double prime. So let's write the V double prime first, minus 0 over 3. Don't make that mistake, ladies and gentlemen. Okay, so let's plug these in. So 1 is equal to V double prime over 3 plus I6, V prime minus V over 6 plus 4. We know what V is, so 1 equals, let's see if we can make any cancellations here. We know what V is, that's 12. Okay. What else do we know? Oh, check it out. We know what V double prime is. So let's put in the V prime plus 6 over 3. So that way we have one equation and one unknown. That's great. So I put the 12 for the V, and I put the V prime plus 6 for the V double prime. And now we could just multiply, let's say, everything by 6. What do we have here? 6 is equal to 2V prime plus, let's see, 6 over 3 becomes 2. This becomes 12. plus v prime minus 12. Yep, so 6 over 6, that cancels. And then don't forget 6 times 4, that's 24. Okay, that's good. So what do you have? 3v prime. Oh, look, these cancel nicely. 6 to negative 18, right? So v prime is equal to negative 6 volts. Okay. If I know v prime, can I get I6? Oh, I can. Okay, so I can go back and plug it back into the Nodal Ohm's law. So what do I get? I get negative 6 minus V, which was 12, right? Yep, 12 over 6. So this is equal to, this becomes negative 18. So I get negative 18 over 6. That's negative 3 amps. So that's I6. And then that comes over here. And I see Ix equals, check this out, negative 3 plus 4. Ix equals 1 amp. Excellent. That's the same answer we got before. Victory, victory. Yes, yes. Okay, so you can see there's so many ways that all should be consistent. What did I do? I solved it via nodal analysis. We did this whole kind of roundabout, reduced this to a Thevenin, and then plugged it back in and got Ix. What else could you do? You could just keep applying Ohm's law and KVLs and KCLs. What else could you do? You could use superposition directly. You have 4 sources and just solve for Ix 4 times. Ix1 plus Ix2 plus Ix3 plus Ix4, right? So hopefully this set of examples helped you out, got to see kind of how my mind works, how I crunch through these problems, and I hope it leads to some success on the midterm. All right, have a great day, and I'll see you in class.